Hello, and welcome to this FMSP Core Prerequisites video. These videos are designed to help you get ahead with independent study of the A2 Core, ready to develop the skills in A2 Further Pure modules. This is what you should already know. Make sure you're really confident with all of this material before continuing with this video. It's best to do the consolidation work as you go along, rather than trying to watch all the videos and then do all the consolidation work. You'll need all of these things, so if you haven't got them ready, pause the recording now and go and get everything together. And make sure you've set aside enough time to do the questions, as well as watch the video. Integration by parts is another new method, but parametric integration is really just an application of integration by substitution. Integration by parts is basically the product rule backwards, so that's where we're going to start. We'll start with an example. We're going to take the function x sine x and we're going to differentiate it using the product rule. So differentiating x sine x, write the first and differentiate the second, plus write the second and differentiate the first. The fundamental theorem of calculus tells us that integration is differentiation backwards. So if I integrate what I ended up with, I get what I started with, but plus an arbitrary constant of integration. I can rewrite that integral in two parts, and the second part is an integral I can already do. So I've now got an expression for the integral of x cos x dx, subtracting integral of sine x dx from both sides, so starting with a product x sine x, I've got an expression for the integral of x cos x. Note that I don't need to put the plus c in on the right hand side anymore because I've got an integral sign there, so the plus c will be absorbed into the plus c from that one. Let's do another example. I'm going to start with x e to the x. If I differentiate that, using the product rule, write the first, differentiate the second, plus write the second, differentiate the first. And then fundamental theorem of calculus tells me that that answer that I ended up with, if I integrate it, I get back to where I started. Plus, sorry, not uv, x e to the x, plus an arbitrary constant. Then it says, hence find just the integral of x e to the x. So if I split that into two parts, and then subtract the second integral from both sides, I get the integral of x e to the x is x e to the x minus the integral of e to the x dx, and I can work that out and put my constant of integration back in again now that I haven't got any more integrals. Now we can generalise this and end up with a formula that will enable us to integrate products. So the general form of the product rule, uv differentiated, is write the first, differentiate the second, plus write the second, differentiate the first. So that means, using the fundamental theorem of calculus, that the integral of u dv by dx plus v du by dx is uv. So writing that formally, u dv by dx plus v du by dx is uv, and because I'm doing this formally, I'm going to put the plus c in. And I can separate that out. Integral of u dv by dx plus integral of v du by dx is uv plus constant. Okay, now if the first integral is the one we want to find and the second one is one we already know, then we can rearrange that by subtracting the known one from both sides and get the formula for integration by parts. Now, it's a bit complicated, but the good news is that that formula is in the formula book, and you don't need to know for the exam where it came from, but most people like to know that these things haven't just been pulled out of thin air. So we'll do an example to show how it works. Suppose we want to find the integral of x cos 3x. We compare that with the left-hand side of the formula, u dv by dx, and we let u equal x and dv by dx be cos 3x. I'm going to need v, so I need to integrate cos 3x, and that gives me 1/3 sine 3x. For the right-hand side of the formula, I'm also going to need du by dx, which is just 1. Now I can substitute everything in. U dv by dx is x cos 3x, which is the integral I'm trying to find, equals uv, so u is x and v is 1/3 sine 3x, minus integral of v, that's 1/3 sine 3x, du by dx was just 1, and here we go. I can do that integral now. That's 1/9 cos 3x. And because I've done all my integrals, I need to put in a plus c on the end. Here's another example. U is x and dv by dx is sine 4x, so du by dx is 1 and v is minus 1/4 cos 4x. Always start by writing those four equations. Then, copying carefully the formula from the formula book, integral of u dv by dx equals uv minus integral of v du by dx. So for my example, that's x sine 4x dx equals uv. So that's x times minus 1/4 cos 4x minus v, that's minus, so I'll change that to a plus 1/4 cos 4x. Du by dx is just 1, so then that's dx. So minus 1/4 x cos 4x, and integrating 1/4 cos 4x is 1/16 sine 4x plus constant. Let's do another example. Here I haven't already said what u and dv by dx need to be. This time I'll tell you, and the next slide starts thinking about how you work that out. So u equals x, dv by dx is e to the 5x. So du by dx is 1 and v is 1/5 e to the 5x. Carefully copying the formula, integral of u dv by dx is uv minus v du by dx. So u is x, dv by dx e to the 5x, this is the integral that we're trying to find, equals uv, so that's x times 1/5 e to the 5x minus integral of v, 1/5 e to the 5x, du by dx is just 1 dx. 1/5 x e to the 5x minus 1/25 e to the 5x plus constant. Okay, what happens if we try things the other way around? This time let u be sine x and dv by dx be x. That means that du by dx is cos x and v is a half x squared. Let's see what happens. Here's the formula. When you're doing lots of examples, it gets a bit tedious writing out the formula every time, but when you're doing an exam paper, there'll only be one question on integration by parts, and it's definitely a good idea to carefully copy the formula from the formula book. So integral of x sine x dx equals uv, so that's sine x times a half x squared minus the integral of v, that's a half x squared, du by dx cos x. Oh dear, this is more complicated than what I started with. It hasn't helped at all. So how do you know which way to go? Well, one of the things is that when you first start, you may find that your first attempt makes it more complicated, in which case you just cross it out and you try swapping them round. As you get better, you'll be able to spot which way is going to help. The general idea is that dv by dx needs to be something that when you integrate it is not going to get more complicated. So something like sine x or cos x or e to the x, which cycle round. U will therefore usually, but not always, be something that gets simpler when you differentiate. Here's an example where it's quite quick to see which way to go. If you try putting dv by dx as log x, you immediately come across a difficulty. You can't integrate log x. Well, not yet. We'll look at it later in the video, in fact, but at the moment you can't, and when you do look at it later, it definitely gets worse, so we don't want to do that. So we'll try it the other way around. Now, this time, the function you've taken for dv by dx is going to get more complicated. But the function you've taken for u gets so much simpler that that doesn't matter. Let's see how this works. If x is natural log of, if u is the natural log of x, then du by dx is 1 over x. dv by dx is x, so v is a half x squared. And let's put that into the formula. So the integral of x log x is uv, that's a half x squared log x, minus integral of v, there you see I've miscopied it because I wasn't actually paying attention when I was doing it, v, a half x squared times du by dx, which is 1 over x. And that gives us just the integral of a half dx, which is dead easy. So integral of x log x is a half x squared log x minus a quarter x squared plus c. Note how easy it was to miscopy that formula, so do make sure that you copy that very carefully from the formula book. If we've got a definite integral, then it's quite straightforward. You just need to make sure that you apply the limits to both parts of the right hand side. Okay, sometimes you need to use integration by parts twice before you can get an integral that you can do. Here's an example. We're going to take u as x squared and dv by dx as e to the minus x. So du by dx is 2x and v is minus e to the minus x. So integral u dv by dx minus equals uv minus integral v du by dx. So the integral of x squared e to the minus x dx is uv, so that's minus x squared e to the minus x minus integral of v, so that's another minus e to the minus x times du by dx 2x. Okay, well that's better, but I can't do it yet, so I'm going to apply the same thing again. This time u is 2x, dv by dx is e to the minus x again. This time du by dx is just 2, and v is minus e to the minus x again. So minus x squared e to the minus x plus uv for my second version, so actually that's minus 2x e to the minus x minus integral of v, so that minus cancels again, e to the minus 2x times du by dx, which is 2. And I can do that one. So I've got minus x squared e to the minus x minus 2x e to the minus x minus 2 e to the minus x plus constant. It's not terribly difficult, but you do need to keep a clear head. Now, this is the best thing about integration by parts. This is really cool. You've not been able to integrate log x before, and this does not look to me like a product, which is what you have when you're doing integration by parts. But actually it is. Log x we can think of as being 1 times log x. I'm going to take u as log x because I can't integrate it, so I'm going to have to differentiate it. Gives me 1 over x. And I'm going to take dv by dx as that hidden factor of 1. Integrate that and I get x. So, integral of u dv by dx equals uv minus integral of v du by dx implies that the integral of 1 times log x dx is uv, that's x log x, minus the integral of v times du by dv, x times 1 over x, well that's just going to cancel out. So x log x minus integral of 1 dx, and I get x log x minus x plus constant. So then by sneakily introducing a times 1, I've managed to use the integration by parts formula to integrate log x. Okay, it's time for you to have a go. Make sure you've got that integration by parts formula in front of you, so take the time to find it in the formula book, but pause the video and have a go at this one yourself. Okay, assuming you've had a go at this, let's have a look at the solution. U is 1 minus x, so du by dx is minus 1. dv by dx is e to the 2x, so v is a half e to the 2x. So my formula, u dv by dx, uv minus v du by dx. So the integral from 0 to 2 of 1 minus x e to the 2x is uv, so that's a half 1 minus x e to the 2x, and because this integration by parts has limits, we need to put that in the square brackets from 0 to 2. Minus the integration again from 0 to 2 of v du by dx. So minus, we'll cancel with that minus to make a plus a half e to the 2x. So evaluating the first bit when x is 2, that gives me minus 1 in the bracket times a half, so minus a half e to the 4. And if x is 0, then that's take away 1 minus 0 is 1, so that's a half e to the 0, plus, and my square brackets because it's a definite integral, integral of a half e to the 2x is a quarter e to the 2x from 0 to 2. So that's minus a half e to the 4 minus a half, because e to the 0 is 1, plus a quarter e to the 4 minus a quarter e to the 0. So that's minus a quarter e to the 4 and minus a half minus a quarter minus 3/4. And that is C. Okay, have a go at another one. Pause the video and try this one. Right, now you've had a go, let's look at the solution. We'll take u equals log x, because we really don't want to be integrating that, whereas differentiating it is easy. And therefore, although it's going to get more complicated, dv by dx is x cubed and v is a quarter x to the 4. So my formula, u dv by dx minus v du by dx so that's integral from 1 to 2 of x cubed log x dx equals uv, so that's 1/4 x to the 4 log x between 1 and 2, take away integral from 1 to 2 of v du by dx, so that's a quarter x cubed. So evaluating, that's a quarter times 16 log 2 minus a quarter log 1. Take away, that's 1/16 x to the 4 evaluated from 1 to 2. So that's 4 log 2. Log of 1, of course, is 0. Take away, put 2 into there, that's 16 over 16, which is 1. And put 1 in, that's 1/16. And I end up with 4 log 2 minus 15/16. And that is C. Okay, that's enough of integration by parts. Let's have a look at integrating parametric functions. Okay, we've got the area under the curve whose equation is y equals 6 minus x squared between the points where x is 1 and x is 2. If we want to find this area, then we calculate that integral, and in general we would write that as the integral from a to b of y dx, where a and b are the values of x at the endpoints. So in this example, the equation of the curve is given in the explicit form y equals a function of x. Here we've got a different function, and it's defined by parametric equations. I've got x and y both in terms of t, and the shaded area is between the points where t is 0.5 and t is 1. So the integral from a to b of y dx, the general form, gives that area, and we have to rewrite that in terms of t. And we do that using the methods that we worked out before for integration by substitution. Y is replaced by 1 plus 1 over t, we know that dx by dt is 2t, so we can replace dx by 2t dt. And the lower and upper limits are the two values of t between which the area lies. So the area is from t equals 0.5 to t equals 1 plus 1 over t times 2t dt. Okay, let's try doing that integral. That's the integral from 0.5 to 1 of 2t plus 2, which is just t squared plus 2t from 0.5 to 1. That's 1 plus 2 minus a quarter plus 1, which comes out to be 1 3/4. As they were using decimals, perhaps the context of the question would suggest that we ought to give that as 1.75. Okay, here's another example. I've got x and y both in terms of t, and we want the integral between 1 and 3. So I need to get dx by dt. That's 1 plus t to the minus 2. So I'm going to replace dx with 1 plus t to the minus 2 dt. Looks a bit horrible, but don't panic. Okay, integral from a to b of y dx is, I'm going from t equals 1 to t equals 3. Y is t squared, and dx is 1 plus t to the minus 2 dt. So that's from 1 to 3 of t squared plus 1. I said it wasn't going to be too bad. And I can do that 1/3 t cubed plus t from 1 to 3. So that's 1/3 of 27 is 9 plus 3. Take away 1/3 plus 1. That's 10 2/3. Okay, you have a go at one. Pause the recording and have a go at this one. Okay, if you've had a go, look at the solution. So the important thing that I need for this is dx by dt. That's 2t. So dx is going to be replaced by 2t dt. So the integral from a to b of y dx is my standard, and in this case it is from t equals 0 to t equals 2. Y is e to the t, and dx is 2t dt. Okay, right, I can do this integral, but I'm going to need integration by parts. So u equals 2t, du by dt equals 2, dv by dt is e to the t, and v is e to the t. So my formula for integration by parts, integration of u dv by dt equals uv minus integral of v du by dt. Okay, so the integral from 0 to 2 of 2t e to the t dt is uv. That's 2t e to the t, evaluated between 0 and 2, minus the integral from 0 to 2 of v, that's e to the t, times du by dt, which is 2 dt. So, if t is 2, that's 4 e squared. If t is 0, then that's 0. Take away. Integrate 2e to the t, and I get 2e to the t. Square brackets from 0 to 2. So that's 4e squared minus 2e squared minus 2e to the 0. So that's just 2. And I get 2e squared plus 2, which is option B. Okay, what now? Don't skimp on this consolidation work. In particular, now that we have covered all the different methods, make sure you tackle some mixed exercises and practice working out which method to use. Ask your A-level maths teacher if you need any extra help, explaining that you need to get ahead with this work. Your FP teacher will tell you when you need to be ready. And remember, you'll gain some time in the spring term, just when you need to spend more time on your FP modules. I hope you found this video useful. The next one continues with differential equations, so do check you need this for your further maths modules before working on it. Goodbye.